There are questions that spark curiosity, questions that inspire wonder, and then there are questions that make even the world's greatest scientists break into a cold sweat. These are the questions that don't just challenge what we know, they threaten to unravel the very fabric of our understanding. Today, we're going to explore one such question. A question so profound, so unsettling, that it sent shockwaves through the scientific community and forced some of the brightest minds on the planet to rethink everything they thought they knew. This is the story of a question that made scientists panic. But before we reveal the question itself, let's set the stage. Imagine you're a physicist in the early 20th century. The world of science is buzzing with excitement. Newton's laws have explained the motion of planets and falling apples for centuries. Maxwell's equations have unified electricity and magnetism. The universe seems like a giant clockwork machine, predictable and precise. There's a sense that with just a little more effort, we'll be able to explain everything. The mood is optimistic, almost triumphant. And then suddenly cracks begin to appear. Experiments start producing results that don't fit the established theories. Light, for example, behaves like a wave in some experiments and like a particle in others. Electrons, which were supposed to be tiny, solid balls, start showing signs of behaving like waves too. The more scientists look, the stranger things get. It's as if the universe is playing a cosmic prank, refusing to fit into the neat boxes we've built for it. The tension builds until finally a single question emerges. A question that will change the course of science forever. The question is deceptively simple. What is the true nature of reality? Is the world made of particles, waves, or something else entirely? And how can something be both a wave and a particle at the same time? This question didn't just puzzle scientists, it terrified them. Because if the answer was both, then everything they thought they knew about the universe was up for grabs. The rules would have to be rewritten. The foundations of physics would have to be rebuilt from scratch. And nobody knew where to begin. Let's zoom in on one of the most famous experiments in history, the double-slit experiment. This experiment is simple in design but devastating in its implications. You take a beam of light and shine it at a barrier with two narrow slits. On the other side of the barrier is a screen that records where the light lands. If light is a wave, it should create an interference pattern, bright and dark bands, where the waves overlap and cancel each other out. If light is a particle, it should create two distinct spots, one behind each slit. But when scientists actually performed the experiment, they got something bizarre. When both slits are open and no one is watching which slit the light goes through, an interference pattern appears, just like a wave. But if you try to observe which slit the light passes through, the interference pattern disappears and you get two spots, just like particles. It's as if the light knows whether it's being watched and changes its behavior accordingly. This result was so shocking that it made scientists question the very act of observation. Does reality exist independently of our measurements, or does the act of observing actually create reality? This was not just a technical problem, it was a philosophical crisis. The idea that the universe might be fundamentally unknowable, or that reality itself might depend on the observer, was enough to make even the most confident physicists panic. The panic wasn't just about the weirdness of the results, it was about what those results implied for the future of science. If the act of measurement changes the outcome, then how can we ever know what's really happening? How can we trust our experiments, our theories, our understanding of the world? The double-slit experiment didn't just break the rules, it broke the very idea of rules. As the implications of the experiment sank in, scientists scrambled to find explanations. Some, like Niels Bohr, embraced the weirdness and developed the Copenhagen interpretation of quantum mechanics. According to this view, particles don't have definite properties until they're measured. The act of observation collapses the wave function, turning possibilities into actualities. Others, like Albert Einstein, refused to accept this. Einstein famously declared, "God does not play dice with the universe." He believed there must be some deeper, hidden reality that explained the strange behavior of particles. The debate raged on with no clear answers in sight. New experiments only deepened the mystery. Electrons, atoms, even large molecules all showed the same bizarre behavior. The more scientists looked, the more it seemed that reality was not just strange, it was stranger than anyone had ever imagined. But the question that made scientists panic didn't just stop at the double-slit experiment. It spread to every corner of physics. If observation affects reality, what does that mean for the rest of science? What does it mean for our understanding of cause and effect, of time and space, of the very nature of existence? These were not just academic questions, they were existential ones. And so the scientific community found itself in uncharted territory. The old rules no longer applied. The old certainties were gone. All that remained was the question that made scientists panic and that continues to haunt us to this day. The panic that swept through the scientific world wasn't just about the double-slit experiment or the strange behavior of light. It was about the realization that the universe might be fundamentally unknowable in ways no one had ever considered. The question, what is the true nature of reality, forced scientists to confront the limits of human knowledge. Suddenly, the comfortable idea that the universe was a giant machine, understandable and predictable, was thrown into doubt. If the act of observation could change the outcome of an experiment, then what else might be slipping through the cracks of our understanding? As the dust settled, physicists began to explore new ways of thinking. Some embraced the uncertainty, while others fought against it. Werner Heisenberg, for example, formulated the uncertainty principle, which states that you can never know both the position and momentum of a particle with perfect accuracy. The more precisely you know one, the less precisely you can know the other. This wasn't just a limitation of our measuring tools, it was a fundamental property of nature itself. The universe, it seemed, was built on uncertainty. This idea was deeply unsettling. For centuries, science had been about reducing uncertainty, about finding the laws that governed the world and using them to make predictions. Now it seemed that uncertainty was built into the fabric of reality. The more scientists tried to pin things down, the more elusive they became. It was as if the universe was playing a cosmic game of hide and seek, always staying one step ahead. The implications of this were enormous. If uncertainty was fundamental, then determinism, the idea that the future is completely determined by the present, was dead. The universe was not a clockwork machine, but a place where chance and probability ruled. This was a radical shift, and it made many scientists deeply uncomfortable. Some, like Einstein, refused to accept it. He spent the rest of his life searching for a deeper, hidden reality that would restore order to the universe. Others, like Bohr and Heisenberg, accepted the new reality and set about exploring its consequences. One of the most profound consequences was the realization that reality might not be objective in the way we had always assumed. In the quantum world, properties like position, momentum, and even existence itself are not fixed until they are measured. Before measurement, a particle exists in a superposition of all possible states. Only when we look does it choose a state. This is the famous collapse of the wave function, and it remains one of the most mysterious aspects of quantum mechanics. The collapse of the wave function raised even more questions. What counts as a measurement? Does it require a conscious observer, or can any interaction with the environment cause collapse? If reality depends on observation, then what happens in places where no one is looking? Is the moon there when no one is watching? These questions were not just philosophical. They had real implications for how we understand the universe. To make matters even more complicated, new experiments kept pushing the boundaries of what was possible. Scientists began to entangle particles, creating pairs that were linked in such a way that the state of one instantly affected the state of the other, no matter how far apart they were. This spooky action at a distance, as Einstein called it, seemed to violate the principle that nothing can travel faster than light. Yet, experiment after experiment confirmed that entanglement was real. The universe, it seemed, was more interconnected than anyone had ever imagined. The panic deepened as scientists realized that the rules of the quantum world were not just strange, they were universal. Everything from the smallest particles to the largest galaxies was governed by the same laws. The classical world of everyday experience was just a special case. an illusion that emerged from the underlying quantum reality. The more scientists learned, the more they realized how little they truly understood. In the face of all this uncertainty, some scientists turned to new interpretations of quantum mechanics. The many worlds interpretation, for example, suggests that every possible outcome of a quantum event actually happens in a vast multiverse of parallel realities. In this view, the universe is constantly splitting, creating new branches for every possible outcome. Other interpretations, like pilot wave theory or objective collapse models, offer different ways of understanding the quantum world. But none of them provide a complete answer. The question that made scientists panic remains open, a reminder that the universe is full of mysteries we have yet to solve. And yet, in the midst of all this confusion, there is a strange kind of beauty. The very fact that the universe is so mysterious, so resistant to easy answers, is what makes science so exciting. Every new discovery opens up new questions, new possibilities, new frontiers to explore. The panic that once gripped the scientific community has given way to a sense of wonder, a recognition that the universe is far more complex, far more fascinating than we ever imagined.